Okay, so maybe let's get started. Yeah, so today we're kind of going to go back to an old topic that we were talking about, some matchings. And most of the time we've been talking about matchings in bipartite graphs, right? That was what we were doing in week 3. But today we're just going to have one lecture on matchings in general graphs, so not necessarily bipartite. And so, yeah, so just to remind you, the notation, terminology. So nu of G is the size of the biggest matching in the graph, right? If you have a matching, a vertex is saturated by the matching if it's contained in one of the matching edges. And the matching is perfect if every vertex is saturated. And something that's, so it's, I mean, a sort of trivial thing, but it's useful to remember during this lecture, is that a matching is perfect if and only if the size of the matching is exactly half the number of vertices. Right? Because, yeah, if the number of edges in your matching is half the number of vertices, then definitely every vertex had to get paired up with somebody, right? Okay. So, yeah. So the kind of theme today is kind of simple thing that I'm sure you've all observed is that, you know, if you have an odd number of things, and you try to match them up, or let's say pair them up, you know, one of them always gets left out, right? Right, probably, I don't know, I remember in school, like, this teacher would say, everybody pair up, and then in the end you have an odd number of people, and it gets kind of screwed up, right? Okay, so this is like the basic kind of idea. And somehow we're going to apply this very basic idea to understand, you know, what is the biggest matching in any graph. Okay, so definition, so given a graph G, so usually we think of, like in pretty much everything we've done, we think of the graphs as being connected. You know, so that there's only one component. Think of this graph as being, well, for the moment anyway, that it has many components, and so we let O of G, so the number of components of G with an odd number of vertices. So generally, I'll sometimes say maybe an odd component. Odd component just means a component with an odd number of vertices. So right, components, I'm not sure that I ever really properly defined this, but you know, if you think of a graph, right, you have, well, maybe I'll just give it an actual example. So if G is the graph that looks like this, for example, right, so the components are the kind of connected bits of the graph, and here you would have, you know, O of G would be 2 because this is an odd component and this is an odd component, but this is an even component, right? Okay. And another just quick definition. Well, it's more of a shorthand. So for a set of vertices, so it's sort of just a shorthand notation that I'll just write G minus U to be the graph, the subgraph induced by all the vertices that aren't in U, right? So you can just think of this G minus U as you delete the vertices from U and all the edges containing them, and you're left with some substructure G minus U. Okay, so kind of a very fundamental result in matchings, going back to, I think, the 1940s, is it's called Tutte's one-factor theorem, because I think people used to call matchings one-factors. I mean, some people still do. And it says that, or sorry, perfect matchings they used to call one-factors. So G has a perfect matching So remember, perfect matching is a matching that saturates all the vertices. If and only if I look at the odd number of components in G minus U, so that's at most U, for every subset of the vertex set. Okay, so let me kind of explain how you should sort of think about this. So it's again going back to this theme that when you have an odd number of things, you simply can't match, you can't pair them all up, right? So, okay, so here's a kind of a picture, right, of the idea. So if you take a set U and you delete it from the graph and you're left with some components. So these are all, these bits are kind of connected within themselves, right? So these are components of G minus U, and there's perhaps some edges from U to these components, right? But there's no edges because so when I delete U, these are components, so there's no edges going from this one to this one, right? So suppose these ones are your, let's say I've got, say, 5 odd components, and let's say I've got 2 even ones, right? Well, so one thing that can prevent you from finding a perfect matching, is like, so if I look at each of these components within themselves, if you try to pair them up with a matching, somebody always gets left out, right? So within each of these parts, if you tried to match them with edges, somebody always gets left out. And maybe even 2 of them get left out, but it has to be an odd number left out, but perhaps even more than 1, but certainly at least 1 always gets left out. And the only way, because there's no edges, between these things or between these things and these things, the only way to possibly hit those guys who got left out is using edges like this, that go from this vertex to U, and these all have to hit separate vertices because it's a matching. So, yeah.
When you say components, can V be any arbitrary?
Yeah, V can be any, finite set of vertices.
Well, in that case, wouldn't G the same for every graph one, graph one?
No, because if I take this graph, for example, so this one has O of G is 2 because there's 2 odd components, right? This one and this one. If I was to connect this all up, though, if I add these edges, connect the components, yeah.
That makes more sense.
Okay, yeah. So if I was to connect these up, then O of G would now be 0 because, there's just an even number of vertices and there's only 1 component, right? Okay, so kind of back to this picture, right? So if you wanted to match everything, all of these guys when you look at this within itself, these guys get left out. The only way to match them is using these vertices, but then you would certainly need to have enough vertices to do that. So one direction of this theorem is kind of easy, that if there is a perfect matching, then every set U must have, the size of U has to be bigger than the number of odd components in G minus U. Because otherwise you simply couldn't hit these, you couldn't match up these guys in the odd components. Okay. And so this Tutte's one-factor theorem says that in fact it's an if and only if. Any questions about this? Okay, so kind of similar to last time. We're going to prove this, but actually we're going to prove it via something which is stronger. So what we're actually going to prove is something called the Tutte-Berge Formula. Which is quite a nice kind of min-max. So this is a theme that comes up a lot in this module, right? You have minimum of something equals maximum of something else. So this Tutte-Berge formula says that for all graphs G, if I look at, so nu of G, which is the max matching size, so this is the kind of max side, is equal to the min over all subsets U of V of 1/2 times size of V plus size of U minus the number of odd components in G minus U. Okay. So in particular, so note that this implies the Tutte's one factor theorem. So T1 FT, Tutte's one factor theorem, right? Because G has a perfect matching if and only if nu of G is a half of the number of vertices of G, right? And this would, so if you apply this theorem, this would imply that, so you'd have to have this side equaling, So by this theorem, this nu of G is 1/2 this minimum. Sorry. This minimum of this 1/2 thing. Right? But that would mean that this always has to be bigger. This always has to be bigger than this, right? Because, if there was some case where this number of odd things was bigger than U, then this would be less than half of V, right? So. Because so if this was equal to this, since this is equal to this, you would have to have this inequality for every set U. Okay, so let's now prove this formula. Okay, so first, so we want to prove that this is equal. Kind of as usual, there's one kind of easy direction and one harder direction. So first we prove the easy direction. So we prove that the left-hand side is at most as large as the right-hand side. Okay, so to do this, so let M be any matching and let U be any subset of the vertex set, okay? And what we want to show is that the size of M is at most, this expression for U. And then certainly it'll be the case that if M was the biggest matching and U was the minimizer of this, then this inequality would hold. So we want to show for every M and U, this holds. Okay, so we can break up, so look at your matching, and let's break it up into 3 pieces, okay? So M, you can write it as M1 union M2 union M3, where M1, so where the edges in M1 are completely within this set U. So edges in M2 are from U to V minus U, and edges in M3 are within, so completely within V minus U, right? So this, if you look at a set of vertices, there's sort of, with respect to that set, there's kind of 3 types of edges, right? So the edges of M1 look like this. They're completely in U. So if this is V minus U, edges of M2 go from here to here, right? And edges of M3 are completely in there. So this is a way of partitioning up the matching. Oops. Okay, so now, one thing is, so if you look at the set U, if I count, so for every edge of M1, so if I count 2 times the number of edges in M1, and if I look at an edge of M2, I count 1 times the number of edges of M2, right? So remember, I'm matching, none of the endpoints, so no 2 matching edges share an endpoint. So if I do this count, this is going to be at most the size of U, right? Because every edge in M1 counts 2 vertices of U, every edge of M2 counts 1 vertex of U, and no vertex gets counted twice. Okay? Some vertices may not get counted at all, but I certainly have this inequality. And then what do I know about M3? Well, so if I look at, so again, it's kind of the same picture as up there. So if I look at G minus U, right, and I look at, so the edges of M3 are completely in G minus U by definition. And if I look at any odd component, you know, so the M3 tries to pair up all the vertices, but on any odd component, somebody got missed, right? Somebody got left out. So if you think about it, this means that, so, okay, maybe I'll write like this. So if I write 2 times M3, so every edge in M3 kind of hits 2 vertices, and you know that in every odd component, somebody failed to get hit. So this must be, at most, the total number of vertices outside of U minus this, because this just says in every odd component, somebody got missed. Right? So therefore, if I take the size of M, so that's M1 plus M2 plus M3, right? So using this first thing, so and I'm sort of going to ignore the 2 because I kind of have that luxury. So I'm going to just write, so these first 2 terms are at most this, and then for this one I'm going to write, so 1/2 V minus U minus number of odd components of G minus U, right? And if you now bring this inside, this is exactly 1/2 number of vertices of V. So V minus U just has size cardinality of V minus cardinality of U. And you have to remember there's this 1/2 here, but just basic algebra, right? You get this. Okay. So certainly the one direction of this equality holds. But again, this is nothing more than an elaborate way of saying this thing from the beginning, right? If you have odd number of things and you try to match them up, you just can't do it. Somebody gets left out. Okay, so now the other direction. So now so we put this direction. So so what we want is to show, or to find, so just to make it clear, right? So what we want to find is a subset of the vertex set such that you have this equality. Right? And that will prove the other direction, right? Because then certainly, yeah, the minimum of this value is at most this. I mean, it'll have to be equal to that. Okay, so we do this by induction on the number of vertices where, okay, the base case is going to be trivial like usual. Well, so the base case where the number of vertices, where the vertex set is just empty is trivial, so let's not bother with it. And so now we just have to do the inductive step. Okay. So also, so by induction, so we can assume G is connected. So this is something I'm not going to go through and verify, but it's kind of easy. So otherwise, like this is the case for most results in graph theory, right? So if G is not connected, just apply the theorem to each connected component. right? Because then you can just apply, well, induction to each component, and then you'll be done. Okay, so G is connected, and we know that the theorem, the statement holds for every smaller graph by induction. Okay. So now let's prove the following claim. So I claim that there does not exist a vertex of the graph such that V is contained in every matching of maximum size. Okay, actually, when I say there doesn't exist such a thing, what I mean is if there did exist such a vertex, then we'll be done. That's what I mean by there doesn't exist one. Because if there did exist one, what I want to prove now is that then we would be done. And actually, I'm going to call this claim 1. Okay, so suppose otherwise. So suppose such a V exists, right? And now think about what happens when I delete it. So if I delete that vertex from the graph, then, and you now look at the biggest matching in the remaining graph, it can't be as big as the biggest matching in G, because, if V is contained in every matching of maximum size, in some sense, when you delete V, you destroy all the biggest matchings in G, because just by definition. So then, if I look at, the matching, the size of the biggest matching in G minus V, so this, of course, just means I just delete the vertex V and all the edges from it. It's going to be, see, if you think about it, it's going to be exactly the size of the biggest matching in G minus 1, right? So if you take any biggest matching in G, you can see when you delete V, it drops by 1. So yeah. So now we apply induction to G minus V to find a set U prime contained in V minus the vertex V such that, so leave some room on the left side here. So the matching, well actually, let me just, so I've already told you that this is equal to that minus 1. So if I write, so this is equal to this, which if we apply this induction, we see that this is equal to the minimum overall, so we found the set U prime such that this thing is equal to 1/2 size of the vertex set of G minus V, which is V minus V, capital V minus little v, plus size of U prime minus the number of odd components in, so I'll write this in a sort of funny way, but in the graph G minus V minus U prime. So that's what the induction will tell you, right? So we're kind of applying induction kind of on this statement, that there exists such a U so that this thing holds. So, yeah. If you take this expression, you move this over to the 1 over to the other side. Oh, yes. Good point. Good. I sort of thought that something felt wrong about that. So thanks. Yeah. Good. Right. So now I put the 1 to the other side in the correct way, since you fixed that mistake. So then what you get here is, so now what I'm going to do is I'm going to let U be the set U prime union V, where V is this guy that we deleted. So now nu of G, when I put the 1 to the other side, it's 1/2. So if I put the 1 to the other side and I pull it into these brackets, remember there's a 1/2 sitting here, right? So it's kind of like adding 2 inside of the bracket, right? It's like a 1 outside and then it's a 2 inside. So that 2 I'm going to use to increase this by 1. So this is the size of V. And to increase this by 1, which is the size of U, right? Because U prime, or U is U prime union one more element. And this can be just written as the number of odd components in G minus U, because this is kind of like I deleted the vertex V, and then I deleted U prime, but you could just do that in one go and just delete U, right? It's the same thing. So this proves the claim, because if such a vertex existed, I would just be done, because this is exactly the equality we were looking for. Any questions about that? Okay. So now, okay, so now we can assume, yeah.
Where did you get, how, we haven't actually proved the equality with size G.
Sorry, can you repeat?
Before we wrote our last slide, we hadn't proved the equality with
With sides?
B, yeah, with size.
Yeah. Oh, but you mean, okay, you mean how the induction works or something, like, yeah, but it doesn't really matter, because so when I say that there does not exist such a V, I'm sort of assuming implicitly that G is some kind of minimal counterexample, but at the end of this thing, we prove that G is not a counterexample, because it has the right, it has this equality, right? So,
Yeah, I just don't understand how it got,
I mean, really, it's just literally by letting U be this set and just moving this one to the other side, and you see that this it just happens to be this. So we applied induction to G minus V to get this equality. So we can apply it to G minus V, right? It's a smaller graph, okay, and then you just define U in the right way, do some algebra, and it works. Yeah, it's kind of a subtle argument. I mean, it's hard to say any deeper reason why this works. It just kind of works, right? Okay. Okay, so in particular, one very basic thing that follows from this lemma. So in particular, G does not have a perfect matching. So PM will just stand for perfect matching. Because if it had a perfect matching, then so it's a matching that saturates every vertex, and so it obviously must have so perfect matching must have the biggest possible size in G, and then kind of every vertex would violate claim 1. So otherwise, in fact, not just one vertex, but every vertex violates claim 1, and we just proved claim 1. Right. So the size of the biggest matching is strictly less than half the number of vertices, because there's no perfect matching. And in particular, this means, because we're dealing with integers, the size of the biggest matching is at most half of the number of vertices minus 1, right? Because that's how integers work. Okay, so now what we want to do is prove a somewhat funny thing, that G actually has a matching of size, well, this size, 1/2 V minus 1. So which will imply, of course, because we have an upper bound on the biggest matching in terms of this, and this would give a lower bound, so this would imply that this must be actually equal to 1/2 of V minus 1, right? And actually, this will imply the whole thing, right? So we'll be completely done once we prove this claim. So let me explain that. But are there any questions about this little bit that I've done there? Yeah. So perhaps before this, I should say, suppose the theorem doesn't hold for G. So, or in other words, suppose no such set U exists, right? Such as, a set at U kind of as in that thing. And in the end, what we found is a set U that satisfies that. And that would be a contradiction, right? Well, by finding this set U, we're contradicting the assumption that no such U exists. I mean, V is just the vertex set of the graph, Okay, let's perhaps, I mean, we can discuss afterwards if you want. Sorry. Okay, so let me explain why this claim 2 implies everything. So in particular, so if claim 2 holds, we just said that then nu has to be exactly equal to half of the number of vertices minus 1. So this implies that, well, it implies that v is odd, right? Because you can't have half of an integer can't equal half of an odd number, so v minus 1 has to be even. And so if we just let u be the empty set, we have that nu of g will be a half v plus size of u, which is 0, minus the number of odd components in g minus u, which is 1, because g has, because when you delete, if you delete nothing, this is just the number of odd components in g, and g is connected, so it'll have exactly one odd component, because this will just be 1/2 of v minus 1. Okay, so if this claim 2 is true, then all I do is I set u to be the empty set, and that finishes it. Okay, so now so let me prove claim 2. So if not, then every matching, then every maximum matching has at least 2 vertices that it doesn't saturate. So unsaturated vertices. So if it's not the case that there's one of size at least half of v minus 1, then it'll always, every such thing will miss at least 2 vertices. So let M be a max matching, and U be unsaturated for M. And among all choices, so such that among all choices of M, U, and V, which have this property, the distance from U to V in G is as small as possible. So it's minimized. Right? So among all the possible matchings, all the possible pairs of unsaturated vertices, we pick them so that they're as close in the graph as possible. Okay. So they're unsaturated, meaning that they're not in any of the matching edges. So if we had, so then we just, so if these guys were actually adjacent, so if they're actually joined by an edge, we just add the edge UV to M to get a bigger matching, and that's a contradiction, right? So definitely these guys can't be adjacent, because otherwise, because they're both unsaturated, we just increase the size of the matching. So we can let T be a vertex which is not the same as U or V, be a vertex on the shortest UV path. Meaning the shortest path from U to V. So yeah, we had to sort of do this first case, because otherwise there might, if U and V are just adjacent, then there's no way to pick an internal vertex on the path between them. But since they're not adjacent, we look at the shortest path, there has to be at least one vertex in the middle somewhere. And a very basic thing is just that since we picked the shortest path, the distance from say, u to t, or the distance from t to v, these things are both less than the distance from u to v, right? Because it's a vertex that's somewhere kind of part way between the two. So it has shorter distance to each of the endpoints, each of u and v. Okay, so now we know that there exists, so by claim 1, there exists a matching M prime of max size which doesn't saturate T. Right? So this is exactly what claim 1 says. For every vertex, there must be some maximum matching that doesn't saturate it, so we can let M prime be such a matching. And among all choices of M prime, choose it so that it has as much, so that it has as many common edges with M as possible. So the intersection with M, between M and M prime is maximum. So it seems we're doing a lot of kind of choosing this so that this is minimum, this is maximum, etc. But it all comes in very handy at the end. So note that, so by our choice of M, we know that M prime must saturate both U and V. Why? Because, well, because we have these, so we know that, you know, T is not saturated by M prime. So if one of these wasn't saturated by M prime, then we've got a maximum size matching where you have, so these guys are closer than U and V, and they're not saturated by M prime. So that would contradict, so otherwise, it contradicts choice of, well, okay, I kind of already said that, but, right? Because, you know, T and U or T and V are closer than UV. Okay, now, so M and M prime, they're both matchings of the biggest possible size. So they have the same size, which implies they saturate the same number of vertices. And you know, this one doesn't saturate U and V, and this one does. So if you think about it, that means that there has to be, so there exists some vertex X, which is not T, not U, and not V, such that X is not saturated by M prime. Oh, sorry, this is not in this set. But it, oh, sorry, it's not saturated by M prime, but it is saturated by M. Okay, so just now the very last step of the proof. So let xy be the edge in M that contains X, and we, sorry. So then, and let E be an edge of M prime containing Y, which must exist by the fact that M prime is maximum, right? Because otherwise I would just add the edge xy into M prime and let M double prime be M prime, so delete the edge E and add the edge xy, and we will have that M double prime intersect M is going to be greater than M prime intersect M, okay? And still, the vertex T is not saturated. It has all the properties that we asked of M prime, and so this will be a contradiction.